Okay, so we completed our discussion of time-like geodesic congruences, focal points, and Hawking's singularity theorem. In principle, there's much more one can say about Hawking's singularity theorem because the version that I discussed assumes globally hyperbolic space-time, and historically Hawking generalized it to the case where you assume only strong causality, which is a weaker condition, and then he even removed that as a condition. You get weaker and weaker results, but there are still results about some geodesic incompleteness to the past. Now, from today, we are going to start talking about the null case, and this is the case of interest for black holes. So what I'll do today and tomorrow is to talk about null geodesic congruences, which we have defined and found lots of properties already. And now we'll talk about their focusing properties. And from there we'll derive Penrose's singularity theorem. And the way things are actually going, it looks very good because we should be able to finish Penrose's theorem by next week. And so 4 lectures from today. And then there'll be 4 more lectures left, and in that time we'll discuss black hole thermodynamics, which will require some study of cosmic censorship also, and then it will be done. Okay. So today's null geodesics, and focusing. As I warned you a few times, the problem with null vectors is that their size is 0, and so we can't make their size in any invariant sense bigger or smaller, and therefore we can't compare the size of 2 vectors very easily. And that's a little annoying because after all, intuitively, if I do have a null vector 1, 0, 0, 1 in Minkowski spacetime, and 1 million, 0, 0, 1 million, these are not the same vector, they are proportional. You would like to say one of them is larger than the other, but it's really not in the invariant metric. So, well, we have to find some workarounds. Now, the key reason why we need that is because recall that in the time-like case, focusing played a key role in deriving geodesic incompleteness. And we want to do the same thing with null geodesics. We want to use focusing of these geodesics, which is relatively straightforward because focusing depends on Raychaudhuri equations, and I've already derived for you the null version of Raychaudhuri equations quite long ago. We'll recall them. But one of the key things about focusing was the following. And here I'll just repeat what we've discussed earlier. Supposing I had a geodesic from P to Q, time-like, and then I had another one which had a focal point with the first one at P prime, then we showed, and it was a very useful result, that you can find a path like this, which is better in the sense that this will have a larger proper time than following P to P prime this way and that way. And so we were increasing proper time. And in the Euclidean case, we were decreasing the distance by taking the shortcut. But in the null case, as I just said, you can't increase or decrease the proper time because it's just 0. So one has to resort to, so cannot be, so this is increasing proper time. And this makes no sense for null. And so we do something a little different, and there are 2 alternatives. One is the classic one used by Hawking and Ellis and Penrose, and Hawking and Ellis in the book, and Hawking's papers, and Penrose and Wald, and that is use achronality. And the second, which is more recent, so this one is Hawking, Penrose, world dot dot dot. And I mean, all the people who come from this community, including Harvey Rial and Paul Townsend, who have written reviews on this subject, all of them use this concept, and I'll review it. And the other is to use promptness. And actually both are equivalent, but physically they look different. And promptness is due to Witten, and quite recent actually. I would say, as far as I understand, it's his reinterpretation of achronality in a way that is quite useful. And it appeared in his lecture notes called Light Rays, Singularities and all that, which is on the archive. And I think those are only 5 or 6 or 7 years old. Maybe 8, but I mean not as old as the works of these people. So in that sense, it's a recent reinterpretation. And this is the one I'll focus on because it's rather nice, and also because I had the chance to hear him describe it in a course in Princeton 3 years ago. Then I'll prove the theorem which says these two are really the same, and hopefully this will help you to also read these references and the same theorems basically. Okay, and what's the idea? Well, let's give a definition and see what it leads to. So we consider a causal path. We don't at this stage insist that it should be a geodesic, nor we insist that it has to be null, but it goes from a point P to a point Q in a manifold. At the moment, we also don't assume the manifold is globally hyperbolic or anything special. We'll say such a path is called prompt if there is no deformation I would rather say there is no other path from P to a point, not from P to Q, but from P to a point S, which is in the chronological past of Q. And usually people say, let's just make it a little more detailed and I'll explain it word by word, to a point, to a nearby point. Okay, so let's start with a path from P to Q. I shouldn't have drawn it straight. So some path from P to Q. So this other path, so first of all at Q, let me construct the past light cone. So this region is I minus of Q. It's the chronological past. It's the time-like past. It's not J minus, but I minus. Okay. I hope you remember the difference between chronological and causal, past and future. Okay. So now let's find a point S over here, which is very close to Q, and let's imagine. Let's ask whether there is or isn't another path like this from P to S, where S is located there. Okay, so we are not comparing two paths from P to Q. So what are we comparing? Well, the simplest way to see it intuitively is that since this is a time-like separation between S and Q, I can as well go to a coordinate system where S is just directly under Q. Okay. Now what in a space-time diagram, if you go from P to Q and I go from P to S, which is under Q, what is the geometry of the situation? Both of us started at the same place at the same time. You reached a certain point in space at a certain time. I, who reached S, I reached the same point at an earlier time. This is something you need to get used to with space-time diagrams. If it's under, it's earlier. So if you just draw the axis here and just think this is x and this is t, then this point, this value of x is the spatial location of both the points q and s. They have the same spatial location. But you reached later and I reached earlier. So I will say that you are not prompt, I am more prompt. Prompt is who arrives earlier. Okay. Now the problem with this, actually Witten almost entirely uses this description, saying that arrives at the same spatial point at an earlier time. But that is of course tied to a choice of coordinate system. If this is true, then more generally is also true that this S can be anywhere in I minus of Q, because you can move it around by a Lorentz transformation. Okay, but the best way to understand it is by viewing it in this form. Okay, now you can see a very funny thing. Suppose this was a null geodesic, the path from P to Q. Can I possibly have another path from P to S, where S is in the time-like past of Q? Intuitively, the only way I could do that is to run faster. But the first one is null. How am I supposed to run faster than that? First one was already running at the speed of light. The second path can't run faster than that. So you would think that there is no such possibility. Okay. So now I'll show you that there are actually two possibilities. So first of all, this definition was applied to any path. So of course for a time-like path, it's fine. Somebody goes slowly from P to Q, I go faster, therefore you are not prompt and I am more prompt. Okay, that's certainly possible. If there was no, okay, so that's for time-like paths. But if P to Q was a null geodesic, then it's very surprising that it may be non-prompt. That's my point. And let's try to show that this actually can happen. Okay, so the first path is called prompt if the second path doesn't exist. That means there's no such path. There's no point S and path from P to S which arrives earlier. Okay. We can also use words like this path is more prompt than that path. And it's always under it, because being under is always being earlier. Yes?
Yes, there is no such S that exists.
Yes.
In the neighborhood of Q.
Yeah, not just S that exists, but there is no path that exists which ends at S in a neighborhood of Q. So we are not going to insist that this whole path has to be in a neighborhood of that path, but we would like it to end at S, which is in a neighborhood of Q.
Can say that the I minus Q intersection with neighborhood of Q is particular.
Yes, you could say that. You could say that, but of course it's a little tricky to quantify, because which neighborhood of Q? I guess what you want to say is that it should be an arbitrarily small neighborhood of Q. Now actually, in most cases, it doesn't really matter, because supposing I could go from here and end up here, which is very, very much before Q, I can simply wait over here and I'll reach Q, because this is the time axis. So if I don't move anymore, I will reach Q. Problem is, all these diagrams are drawn in Minkowski spacetime, because it's the only thing we can represent on a board. So we want to sort of avoid the possibility that some bizarre thing might be happening in between. So for this reason, we say slightly before Q. But actually, I personally don't think it matters a whole lot, whether it is slightly or a lot before Q.
It doesn't matter anywhere, it's in I minus Q, because by a coordinate shift you can...
By a coordinate shift you can actually, that should be, yes, exactly. And then you can wait. It might be that the proper time is very large, but then you can't change by coordinate shift, but then you can just wait till you get there. Yeah. Okay. So
a simple example of two null rays, one being more prompt than the other, is gravitational lensing.
Exactly what I was going to say now. It's exactly gravitational lensing, and it's true, and it's what you said, but it's still very baffling. So I have some star, then I have some matter, But the matter I'm assuming for this discussion is purely gravitating matter. There's no electromagnetic or any other effect or strong or weak interaction effect. It's only gravitating. And there are photons coming out from this. And we know experimentally that light, of course, first of all, we know both theoretically and experimentally that light bends due to gravitational attraction. But of course, remember that this bent line is actually what is a straight line in gravity. That's a geodesic. It's a null geodesic because light in gravity always travels on a null geodesic. And here's a different one. Okay, this is not a space-time diagram. This is a spatial diagram where I'm sitting on Earth and that is a star. Okay. Now the point is that I can record the image of the light because it's light. And I see some image which shows me 2 copies of this star or multiple copies, because when I see something like this, I mentally I extrapolate this back here and I see something like a star there, and this one I extrapolate and I see a star there. And then observationally I notice that, well, it's exactly the same star. How come it's showing up twice? It's not 2 different stars. It's just that star, but because of this bending effects, it's showing up once there and once there. So far so good. On a still image which my telescope produces, there are 2 images or many. Actually, in general you get rings and all kind of things. But if I actually time the time when this image reached and this image reached, they could reach at different times. And then I have the example of a non-prompt and a prompt geodesic. So what would happen is that I on Earth in my local coordinate frame measuring time with my ordinary watch or something little better would notice that one image, maybe this one, arrives here at some time t0 and this arrives half a second later. I'm just making up a number. I have no idea what the number is, but let's say it arrives half a second later. But then it's exactly this situation because one of those paths is going from P the star to Q, me on Earth, and the other path which arrives half a second, one is going, so one path is going from P to Q, let's say, and the other path which is earlier is going from P and reaching at S. And S and Q are both me. Okay, except that S is me at time t0 and Q is me at time t0 plus half a second, just half a second later. So in that case, the one which reaches first is the prompt one and the others are non-prompt. But what's so bizarre is that they've all taken 0 proper time to reach me. It's possible. You'd almost think it's not possible, and the reason why you would think so is that in Minkowski spacetime it's not possible. So in Minkowski, all null geodesics are prompt, and anything which isn't prompt, and that's that. Okay, because in Minkowski I have a very simple light cone, and the null geodesic, if I have a point here on the boundary of the light cone, so this is on del J plus, then I can reach it by following the exactly straight line along the light cone, and there's no other line which has any chance of reaching earlier, because to reach earlier I would have to go outside the light cone in space-like, and that's what I can't do. Okay. In fact, more generally, to have a prompt path for even one, so there could be situations where there's no prompt path. Okay, I'll give you a simple example where there's no prompt path, or it's almost trivial. Let's take P and Q to be just time-like, separated only in time. Okay, then if I do nothing, I'm already at that place much before the path which goes from P to Q, and So there's no concept of promptness really, it's just trivial. So to have a prompt path,
why is it trivial? There will still be some path which will have the minimum proper time.
yeah, so yes, but that path in this example is just no path at all.
It is still a path, right? Even if it's just a straight line, it is still a causal path.
Yeah, we are not comparing proper times. We are simply comparing the promptness is just a statement that there is a path which arrives sooner to the same place. So in the case of time-like separation, the path which arrives sooner is just the most trivial path you can think of. Actually, yeah.
There's still a concept of that trivial
Good.
path will be the
Okay,
prompt.
the trivial path is prompt, very good, but it doesn't reach Q. So therefore, we are trying to find a condition where Q should be for the path to be prompt. And so to have a prompt path from P to Q, we must have Q in the boundary of J plus of P. To have any causal path from P to Q, of course, Q must be in J plus of P. But if it's in the interior of J plus of P, just by going to a little local Minkowski neighborhood of it, you can see that there's always a way to speed up a bit and just reach earlier. Okay? Because if it's in the interior of J plus, then it is time-like separated from you, and then you can always try to go faster. It's only when it's on the boundary, then you can't go faster. And so these are two different statements. One is that all null geodesics are prompt in Minkowski, and there also this second statement is true. Q has to be on boundary of J plus, and the unique geodesic is null geodesic is the straight line joining them, and it's prompt, and there's nothing more to discuss. So therefore we see that it's only in non-trivial spacetimes where you can have a non-prompt path. So gravitational lensing, of course, I haven't done any calculation for you to show that it is possible, but experiment shows that it's possible because actually it's done and we actually know the result. Another one where we can instead show you theoretically that it's possible is to imagine 1 plus 1D Minkowski spacetime, but with the space direction being on a circle. Okay, here the existence of non-promptness will be a consequence of the topology of it, because there is no interesting geometry of for a cylinder, but the topology, the fact that it has a circle in it, is the fact that is the non-trivial thing. Good. So here, imagine that I consider a null geodesic. First of all, let's look at the structure of, I think we've done this once. So let's revisit the structure of J plus of some point. So let me just take an arbitrary point P over here. Now as you can see, there's a light cone going out from it. Okay, and then it goes behind like this. Okay, and then the actual J plus of P is the entire future of all these four lines. Two of them going like this, two going from behind, and everything about that. That's J plus of P. Now imagine that I put up my point here, Q, and I consider a null geodesic which is going like this and then like this. Okay, I'm sorry, I'm violating my own convention. If it's at the back of the cylinder, I'm going to make it dotted, and it's going to reach Q over here. Okay. Now, if I want to, so Q is at the back of my figure, but notice, so this is my first, this is the first geodesic from P to Q. Can I find a point S which is in the causal past of Q? I can actually find a point S which is just directly in time in the past of Q at the same spatial location. It's also on the back of the cylinder at the same point relative to this circle, but much earlier in time than that. And this geodesic will reach S while this geodesic is reaching Q, never passes through S, and S is much earlier than Q. And this S is clearly in I minus of Q. So in that case, this geodesic on the right is prompt, or at least it's more prompt. Turns out it is prompt, but this one is non-prompt. So topology of the cylinder has done this for us. It's made one path, both are null geodesics. One is prompt, one is not prompt. Now notice a very amusing thing about this. What stands out about this figure? These two null geodesics have a focal point there. Right? We define focal points. It's just where two geodesics meet. In this case, two null geodesics are just meeting at that point. That's a focal point. Q is beyond the focal point. Okay? And in this example, the geodesic to Q is non-prompt only as long as Q is after the focal point. If you drag Q from there to say here, the geodesic will be prompt, the same one. The same path which we are following to get to Q, if Q was here, we would follow this path and this would be a prompt path. There's actually no way to get here earlier. So the promptness failure is occurring after a focal point. And this is only an example. So failure of promptness occurs beyond a focal point. This is only an observation, but in a few minutes we'll argue that that's the general situation. In any manifold, when two null geodesics have a focal point, then continuing beyond that focal point will lead to a non-prompt curve, and there will be a way to find a more prompt curve. And it's the analog of what we did for time-like, but it's really an analog because what we've done is to, instead of focus on pairs of curves between the same points, we are now focusing, we'll see what we do to smooth out a focal point. That if you remember in the time-like case, when there is a focal point, we smoothed out something. We switched to another geodesic, we smoothed out the kink and all that. We'll do all that here, but it will be slightly different and it will be based on promptness. Okay. So, so this is one general property, though we haven't proved it. There's another general property which we also haven't proved in the general case, which is that for a non-prompt null geodesic, an initial segment is prompt, always. Again, it's true in this example. So the initial segment of the null geodesic from P to Q is this much, let's say, okay? And this is prompt, I just argued. But it's a general rule which we have to prove. For any non-prompt null geodesic, there exists an initial segment which is prompt. Now in general situations, I may need to impose some causality constraints on the space-time, which I'll do as we go on. For the moment, we're just working with Minkowski examples, so we didn't have to say anything more. So now, oops, stop it. Let me also prove another theorem. Let me prove a theorem and then we'll continue. Then we'll prove these two. These are both also theorems. Any questions so far? Then I can continue. I'm simply listing properties of prompt geodesics and non-prompt ones. Okay, so let's ask a question. There's a converse to this. We said an initial segment of a non-prompt geodesic is always prompt. But supposing if we have a prompt geodesic, can an initial segment be non-prompt? Another way to put this is, supposing I have a non-prompt null geodesic, can it become prompt by extending it? Okay. Now, if you analyze this in the language of someone who's running, it's like saying if someone decides to run too slowly in the beginning, can they make up so that their average speed is the best possible? Okay, and clearly that's not true. And in fact, you will see that once it is, if an initial segment is non-prompt, there's no hope to make it prompt by extending the curve. In the time-like case, you can see the analog of this. If one person is if both people are able to run at the speed of light, and one of them chooses to run at a slower speed for some time, and the other guy is running at the speed of light, then the first one isn't going to speed up and catch up because they would have to run faster than speed of light. That's not exactly what we're talking about here, because here all the segments are running at the speed of light, but the geometry or topology or whatever of non-promptness will make it impossible for an initial segment to improve its behavior by becoming prompt. So let's prove this one. This is the question. So let's actually restate the question as a theorem. If we have a prompt geodesic, an initial segment cannot be non-prompt. Or we can, I think, much more elegant way to say it is, if an initial segment is non-prompt, then the geodesic cannot become prompt. So let's try to show this in diagrams. So here's my initial non-prompt segment. Let's say P to P prime. Okay. Sorry, P1 to P2. And suppose this is non-prompt. That's what we are given. This is the initial segment. Since it's non-prompt, there is another curve that goes up to here to P2 prime, which is before P2. Okay, this one is more prompt, showing that this one is failing to be prompt. Now somehow I extend this in whatever way I like to a point P3. To prove the theorem, I need to show that this curve, which went from P1 to P2 prime, can be extended so that it reaches before P3. But now it's sort of obvious from the figure, because in some suitable coordinate frame, P2 prime is a small amount of time before P2. All it has to do is to follow the exact same path as the path P2 to P3, but remaining at that slightly earlier time till it reaches P3 prime. Okay. So this is a way to show that you can actually be more prompt than the original path. Once you have reached somewhere, it's like again a runner at a halfway point is ahead of others, then in principle that person can remain ahead of the others all the way till the end by simply making sure that he or she stays in front. Just don't let the other person pass you. letting the other person pass you would amount to these two lines crossing. And since this may be in a general manifold, there may be all kinds of topological things happening, but whatever obstacles or topology or effects this line P2 to P3 is encountering, by staying just behind it, below it rather, which means ahead of it, you will encounter the same roughly. So you can actually imagine, if this is arbitrarily small, you can imagine this to be a Minkowski neighborhood and then just keep extending that. This part you cannot see in a local Minkowski neighborhood. The fact that there is a null curve and another null curve reaching earlier, you simply can't see. So we have to accept that from here to here something has happened which we can't really draw. This drawing is just a schematic, but from here to here we can actually see it. It's just the statement that if one point is earlier than another, it can be made to remain earlier than the other, no matter what. Okay. Okay. Now, in fact, it follows, in the definition of promptness, we never really wrote geodesic, but it is true that every prompt curve, I'm not writing causal because that's in the definition of prompt, must be both null and geodesic, so a null geodesic. So this is the reason why initially I said that for there to be a prompt curve, the destination spacetime point Q better be on the boundary of J plus. Okay? Because if it's not a null geodesic, then that means it's not everywhere null. That means it's somewhere time-like, because it's certainly causal. I'll write it anyway, though it's redundant. Since it's causal, wherever it's not a null geodesic, it's time-like. And once it becomes time-like in between, it has lost the race. So here's something trying to be a prompt causal curve, but for some reason it decides to go time-like in between here. So I simply follow it. And at this point, I don't make the same mistake. I just continue like this and I reach ahead of that person. So the arguments all involve this kind of diagram. Okay. Now we can prove the theorem. An important theorem. A null geodesic is prompt if and only if it is achronal. Okay, so since it's an if and only if statement, we have two things to prove. So take a path assumed to be prompt but not achronal. So this is a hypothesis which violates the statement of the theorem. If we can show this to be a contradiction, then it means every path which is prompt is achronal. Then we need to prove the converse direction theorem. Okay. Now let's recall what achronal was. I should have said that 5 minutes ago. Achronal means, so let me also just read the definition so that yes. So a subset of the manifold, any subset, it doesn't have to be a curve, it could be a hypersurface or any other manifold, or indeed it could just be even set of points, but it's trivial there, is achronal, means everywhere space-like or null, and no two points can be connected by a time-like path. Okay, now I've taken a path which is prompt but not achronal. So let me sketch that path. This is my path which is prompt but not achronal. I should never draw straight lines here. Please keep reminding yourselves that most of my diagrams have nothing to do with flat space-time. Just hypothetically now, as per this assumption, there is this path is not achronal. So that means that there's a time-like segment. Let me go down a bit and a little bigger. So here's my path from P to, let's say, I don't know why, but I labeled it P3. This is my full path. It's prompt between P1 and P3 by assumption, but it's not achronal. Therefore, there is a diagrams are so bad. I want to make this look very null. Now there is a pair of points, call it P2 and Q, such that there is a time-like path. This is the non-achronality of the P1, P3 curve, that it's not achronal, therefore it can be connected, two of its points can be connected to each other by a time-like path. Okay. Now, if a time-like path exists from P2 to Q, just that path, I know that it's not prompt. No time-like path can ever be prompt, because this means that Q is in I plus of P2. Right? The fact that there is a time-like path means Q is in I plus of P2. And now, if that is so, it's not prompt, that segment. So there is something which is more prompt, and that will reach here, under it, at a point. This is the point S in the past of Q. Okay, which is more prompt. And now the same story. Once I have reached S before Q, I just keep going and I'll reach some new point S prime before P3. So that means the whole original path P1, P2, Q, P3 was not prompt, contrary to the assumption. So this is a contradiction. Therefore, we have proved that a prompt path must be achronal. Somehow the key difference is just a difference in emphasis. Promptness has to do with reaching sooner. Achronality has to do with time-like paths between them. But you can clearly see in one direction that the time-like path is ruining your chance of being prompt, because you can arrive sooner. And once you arrive sooner in any segment, we can also just recycle an older theorem, which is that if an initial segment is not prompt, it can't catch up and become prompt. Okay, that's in one direction. Now we have to do the converse. For the converse, we suppose that a given geodesic is not prompt. And what we want to prove is that it's also not achronal. In that case, combined with that one, we have proved that prompt and achronal are if and only if. So it's non-prompt. So this is my original P to Q. Being non-prompt means there is another path to S, which is before Q. Okay. Now, once I have reached S, which is slightly before Q, this is me, the runner who has run faster before that one. I simply sit on the ground and wait until the time passes and the other person shows up. So I complete my trajectory by going like that, which is purely time-like and certainly allowed. So the one person has completed PSQ and reached Q, while the other person went P to Q. Okay. Now, there's a theorem which actually I'm not going to prove, and it's just a little subtle, but I think you can sort of see intuitively why. Given a curve which is partly null and partly time-like, you see that this segment is null because this is a more prompt path than that. This segment is time-like. And the theorem says, and actually maybe I proved something similar. Theorem 4.4, yeah, I did prove it actually. That given an inextendable causal path, there exists an inextendable time-like path in the future of that causal path. So that means that I should be able to take this path plus this time-like segment and round it off to get something like this. And this one will be causal, will be fully time-like. So we used non-promptness of P to Q to argue that there is a path P to S where S is before Q, and then we added this segment and said, okay, rounding this second curve means that there is a dotted line like this which is fully time-like. Okay, and if it's fully time-like and it's joining P and Q, then PQ is not achronal, because achronal means there should not be a time-like segment joining any two points. So PQ is not achronal. So we have shown that non-prompt implies non-achronal and prompt implies achronal. So this proves the equivalence. But again, I urge you to think about this, because it's not, I mean, they're not the same thing in the sense, they are equivalent definitions, but they don't look the same. The spirit of one is being able to connect 2 points in a manifold by a time-like curve. The spirit of the other one, namely prompt, is just being able to reach somewhere earlier than someone else. Okay, good. Okay. Now another interesting theorem about promptness. So we are just collecting a lot of results, and they'll all slowly be applied. Please stop me if you have any questions. I don't believe anything I'm doing is completely obvious, and as you can see, it really goes to the heart of space-time physics in a curved manifold. It's the weirdest geometrical thing that you cannot really imagine in any normal physical situation that is familiar to us. So any questions?
So this theorem connects that Penrose and Hawking's formulation.
This theorem connects the formulations, but because the spirit of promptness and the spirit of that achronality is slightly different, the way the theorems that we will do later will be formulated will also be slightly different. At all stages it will be equivalent, but the look is different. It really comes as a bit of surprise in the beginning that you're not even trying to compare space-time curves between the same space-time points. You're trying to compare one with another one which is simply reaching the same space point earlier in time. So, yeah. Okay. Okay, now, and this is actually very important. So, again, it can be written as a theorem. This I already said it, but now it's because now I'm going to prove it. Maybe I wrote it already. I think it's this one. Yeah, it's this one. For a non-prompt null geodesic, an initial segment is prompt. This I haven't proved yet. I haven't actually proved either of these yet. But this one I will prove after I discuss focal points. So far we are staying away from discussion of focal points. So let's prove this one first. An initial segment is prompt even if the whole thing is not prompt. And that actually is not completely trivial because it's not true in arbitrary spacetimes. It's actually true only if the spacetime has some minimal requirement called strong causality, which I probably defined, but I'll definitely do it again. Strong causality is implied by global hyperbolicity, so it will also be true if we have globally hyperbolic spacetime, but we only need strong causality. So let's write the theorem. In a strongly causal spacetime, so it's the same result which I just showed you down there, but I'm just restating it a little more formally and also stating the condition under which it can be proved. Every non-prompt geodesic has an initial segment that is prompt. Okay, now strong causality has actually, there are two ways to state the definition. And I'll need to just find the place, I should have linked it from here. Where is the definition? Yeah. Give me a minute, sorry. Actually, I should be able to find it in a search. Yes, good. A spacetime is so, recall, digression again. A spacetime is strongly causal. If you remember, this was introduced in order to get rid of closed time-like curves and even curves which are arbitrarily close to being closed time-like curves. If for every p in the manifold and an arbitrary open neighborhood there exists a sub-neighborhood B subset of O through which we'll draw it and see how this works, through which no causal curve passes more than once. Before I try to illustrate the general situation, let's imagine we have the following situation. We have a point P and we have a causal curve. Now, of course, in this diagram, it doesn't look like it's causal because it's going forward in time and appears to be coming back, but it's some weird manifold, maybe it can do that. If it would come back to exactly P, we would just call it a closed time-like curve, okay? But supposing it does the following thing, it comes back and then it slowly kind of runs out of energy just before reaching P. But not before reaching P, it comes arbitrarily close to P. So in a way, you can say that this point is connected on this side, but this side is, these two are not joined very precisely, okay? But arbitrarily close. Now you can see this is not strongly causal, because take a neighborhood of P like this, O. Now I should find a smaller neighborhood where every causal curve passes through more than once, but in this neighborhood it has passed through twice. So this is a kind of prototype of what is not strongly causal. It allows for nearly closed time-like curves when it's not strongly causal. So if it is strongly causal, we forbid nearly closed time-like curves. Okay. And there's a nice lemma in Bald's book which explains that global hyperbolicity directly implies this result. And if you remember global hyperbolicity, we knew that that it obviously bans closed time-like curves because they are supposed to intersect the Cauchy surface, and if they are going to be closed, then they could very well be closed, just not intersecting the Cauchy surface. But in fact, it also implies this. Yeah.
Involved strongly causal rules out closed time-like curves only. And stable causality rules out almost closed time-like.
Is that right?
Yeah, stable causal, like is a diagram, like you can see as a cylindrical Minkowski, and he removed one point from that, and at the point removed around it is strong.
But this definition of strongly causal, I thought
it's right. Definition is right.
Right, and it removes closed time-like curves.
It removes closed time-like curve.
Yeah.
Even if you have arbitrary closed time-like curve, you can expand your deform your space-time and get a closed time-like curves.
Yes.
So that condition is removed by stable causality. That even any arbitrary deformation, the time-like curves will not meet.
Okay. That is another condition. Oh, good. Good.
Hierarchy.
Okay. But here, strongly causal is what I said. Oh, good. Okay. Yeah. I see your point. That in order to rule out closed time-like curves, I need stable causality.
Almost closed time-like curves. We need stable causality.
What does this rule out?
This
just
closed
time-like curves. Okay, I am still not convinced of that, but I will double check and tell you tomorrow. But probably maybe you're right. Anyway, now now there's an equivalent definition of strong causality, which says that. And it's an exercise which you should do to prove that these two are equivalent. This says every point P has an arbitrarily small neighborhood O such that every causal curve between Q and, I'll draw it again, every causal curve between 2 points, need not be P, Q and R, which are 2 points in O, is fully contained in O. So here's my point P, here's a neighborhood O which I choose to be arbitrarily small, and this guarantees me that any pair of points Q and R, all causal curves between them are fully inside O, which actually means the whole causal diamond. So it's too small. O is supposed to be small, but I can't draw it very small. So here's P somewhere. This is a neighborhood. And now the statement is that pick any Q and R and let's draw their causal diamond. This is the causal diamond. It's the intersection of the causal future of Q and the causal past of P, that thing. And so causal curves between Q and R have to sit inside that. So the statement is that there is always a neighborhood of P such that every causal diamond for a pair of points inside is fully inside O itself. Okay. So this is opposite of, in a way, this is what ensures strong causality, because if you don't have this, then you can have, so if you have this, then you can't have this thing of causal curve going out and coming back into the region. So I'll let, I think instead of going on explaining it, I'll leave it to you to work out this fact. It's quite straightforward, and it's the property which we are going to use. The fact that there's a neighborhood of every point P such that every pair of, all causal curves between a pair of points are fully contained inside that neighborhood. Okay. Now with this requirement, what are we trying to prove? We are trying to prove that an initial part of every non-prompt null geodesic is prompt. And for that, let's consider a point P1 and another point P2 here, which is in J plus boundary of J plus of P1. This is boundary J plus of P1. And supposing I have enclosed P1 in a small neighborhood, let's call it O. Then for a sufficiently small neighborhood, I can imagine that this part is Minkowski. And in Minkowski, there's a unique null geodesic between P1 and P2. Okay. So you might think this is already the proof of my theorem. I just look at the initial part of my, hypothetically I have some null geodesic which is somewhere doing that. I look at the initial part, enclose it in a open set, and then I say, well, it looks like Minkowski, so therefore there is a unique null geodesic from P1 to P2. The problem is, in a generic space-time, if O is sufficiently small, I can't rule out that there might be something which exits from O and comes back into O, which is more prompt. Okay, this is why strong causality has to be imposed. Okay, so then once you can rule that out, then the fact that this is ruled out by strong causality. Because all causal curves for this small neighborhood O, all causal curves between P1 and P2 are fully contained inside O. And coupling that with this local Minkowski neighborhood, we see that you actually have an initial segment which is prompt. So theorem is proved. And I already told you that in the cylindrical example, you can see clearly that there is an initial part which is prompt, while the whole thing is not. Okay. So, to conclude in the next 5-10 minutes, we'll simply talk about focal points and try to write down. Now, if you remember, in the time-like case, we had actually 2 rounds of discussion on focal points. One was what you might call a more informal discussion with words, where we drew pictures and smoothed out things to increase the proper time. And then we gave what is a more formal and more rigorous definition in terms of Jacobi vectors and geodesic deviation equation. But for the null case, I'm going to stick with only the informal version, and we'll use that till the end. The formal one actually is not so easily found. Wald has a version of it, but this whole geodesic deviation approach in the null case is a little more complicated, and so far at least I haven't worked it out for myself properly. So I'll content myself with the informal version. Okay, so this is the last point to discuss today, focal points for null geodesics. And the actual existence of a focal point is exactly the same as for time-like case. Just imagine that there's a null geodesic going from P to Q, and there's an intervening point, let's say P prime. And now these are all null, everything. This is a null geodesic by itself over this much segment. This is also, therefore, this segment, this whole thing has a focal point for these two. And then we continued, the first one continued after its focal point. And as we can, of course, the total proper time from P to P prime is 0, from P prime to Q it's 0, from P to P prime this way it's also 0, all are 0. But they are all in some sense equivalent, that this is a deformation of that, which has the same whatever, it's null. Okay. Now, we want to show that P to Q is no longer prompt, if this is true. Okay. And of course, we again use the kink. But what we do with the kink is a little different. Since there is a kink, this one cannot be a geodesic, because a geodesic is a path. It is a geodesic here and it's a geodesic here, but the whole thing joined is not geodesic. And that's because a geodesic by definition has its tangent vector propagated parallel to itself. And there is no way that the tangent vector, when we approach P prime from this side and there is going to be parallel, because there is a kink. Kink is where something must change discontinuously. Okay. So we can try to smooth out that thing, but we are not going to smooth it by joining a dotted line from here and ending at Q. Instead, we'll say that, well, if this is so, then there must be a null geodesic which simply goes like this and reaches the point S in the past of Q. So the smoothing prescription does not smooth out to find a new geodesic from P to Q, but rather finds a new geodesic from P to S. But the fact of smoothing is the same and the motivation is the same. If you have a pair of null geodesics joined at a kink, there has to be a smooth version of it, but which is going to smooth out the kink, and then once it's done that job, it will simply stay in the past of that one and end up at S, which is in I minus of Q. And this existence of such a thing is the proof that the original P to Q was not prompt. So again, this you can find more details in Witten's review, but the basic idea is just that. A focal point spoils promptness, and this is the proof. Okay. So it actually was shorter. I think maybe I should have said a few more words about it, but I don't actually know a much better way to say this. What is interesting is, of course, you could argue that this means that when there's a focal point, this line P to Q cannot be achronal, because by equivalence of promptness and achronality, that should also be true, that P and Q fails to be achronal. So now you should be able to find, given a kink, you should be able to find a time-like curve which joins 2 points on the original curve. I guess it's something like, if this exists, then we just close it there, and then again we use that theorem that in its future there's a time-like curve. And then this is also null, but now we have null plus time-like. Again we smooth it to get all time-like, and then we prove that PQ is not achronal. So there are 2 steps. In a way, the prompt versus achronal is exactly just forgetting this last segment and the smoothing theorem. If you always have that in your mind, then it's very manifest that prompt and achronal are the same thing. Okay. And the last thing, which is sort of straightforward, and we've done it many times before, if I have some sub-manifold, and a point P, then I can look for null geodesics from the sub-manifold, from any point of the sub-manifold, let's call it S, to the point. And if any 2 exist which focus at the point, then that's a focal point for this class of geodesics. And this is not necessarily going to be a null. In fact, this is in general going to be space-like. So you can, if you want a better representation, you can think like this, because this is actually the situation relevant for Penrose's theorem. Let's not be an arbitrary submanifold, let's have a codimension 2 submanifold. We've drawn this sort of picture many times. Once there's a codimension 2 submanifold, that means there are 2 dimensions missing in it, so there are 2 normal directions, but this is space-like. We're taking it space-like. And we've seen repeatedly that given a space-like submanifold of codimension 2, there are 2 directions going out, which you can treat as either one space and one time, or both null. Take the outgoing space and time direction and take plus and minus, and you'll get 2 null directions. In the past, we have said one was called U and one was called V, and we have worked with them quite extensively in the context of Schwarzschild causality, the eternal black hole Penrose diagram, and so on. So now we have to, that means we can have null geodesics in that direction, and we can have null geodesics in that direction. And these, I probably have interchanged them. If this is the coordinate, then this should be V, which is ingoing, and this should be U. But this is V equals constant, and this U equals constant. And so here, supposing I focus only on the V geodesics, then those are the ones which will focus like that. If I focus only on the U geodesics, those are the ones, and they can focus like that. What tells us whether they focus or don't focus? Raychaudhuri equation as before, but the null version, which I've already derived, but I'll write it again probably tomorrow. And the important thing to realize is that these always intersect S orthogonally. And we did that construction as I said. In general, they intersect orthogonally, and the reason is that just to be a geodesic from here to here requires an orthogonal intersection. In the time-like case, that's very obvious, because if it intersects at an angle, then by shifting the angle to be 90, you can just make it shorter. The analog here is that if it intersects at an angle, then by slightly shifting it, you can show that the original one was probably not prompt. Okay. So this defines focal point between manifold and manifold, focal point in the future of the manifold. And we can also define the concept of prompt and non-prompt as follows. Same manifold. In fact, I can just write over this one. Pick any one of these U's or V's. Let's say U's for now. And just let's have one null geodesic which intersects the manifold orthogonally and reaches here. And this point I'll call Q. What criterion should I use to define to say whether this one is prompt or not? So the answer is, it's non-prompt if there is another geodesic starting from the manifold but not necessarily the same point and reaching the S in the past of Q. The difference is, earlier we wanted all geodesics to start from a common point, but when we do manifold to a point, we allow them to start in a different place. So this gives me, I don't know if it's worth writing. So a null geodesic from this S, I'm sorry to confuse, I don't want to confuse it with that point S. Maybe that was a bad choice. I think let's just consistently call this point Q prime. That's a better choice. I should change it in my notes also. From the submanifold S to Q is prompt. This is the definition. If there exists no null geodesic, well, actually no causal curve. Again, we don't have to say null geodesic. Causal curve. If there exists no causal curve from S to Q prime in the time-like past of Q, and I'm not writing it, but sort of slightly to the past. So it's this analogous definition, and actually it's the more important focal points both in the time-like case and in the null case are not the ones for geodesics starting from a common point, but geodesics starting from a common surface. In the time-like case, the geodesic starting from the surface was simply anyone, anywhere in the present universe at this time, trying to go back into the past, following a curve back into the past. Those would be the geodesics that then focus and destroy geodesic completeness. Here what will happen is that when you have a collapsing shell which makes a black hole, then there will be a spherical surface such that all the geodesics to the future come to focal point. So the inside of the black hole is geodesically incomplete, which is what we mean by there being a singularity. The surprising thing in this case is that, first of all, this thing is eventually going to be a sphere, but you would always think there's an outward direction from the sphere and an inward. And in a space-time diagram, inward is slanted this way and outward is slanted this way, but we'll see that in black holes, both the inward and outward can be both slanted this way, and that's what causes the black hole to be a black hole. So that's tomorrow actually. Any questions? So then I'll stop here.